Now, in our second topic of thermochemistry, we're going to look at how can we quantify this energy. So we have a bit of a sense that energy can be transferred back and forth, but how can we understand that more numerically? Anytime we're quantifying something, it means that we're using numbers. And we like numbers, of course, in science because they are reliable and they are ways that we can cut through bias and help to improve understanding. So let's look at our chemical universe. We have a little universe here, and this would be true for the big bad universe. This would be true for a universe that is just a kind of a chemical experiment. We always have two parts. We have the thing that we're looking at. That's the thing that we're trying to study. We'll call that our system, our chemical system. And the system can interact, can lose energy, or it can gain energy from the stuff that's around the system. And so the stuff that's around the system we call the surroundings. Right? Energy can be transferred back and forth. If it's an exothermic reaction that's happening in my chemical system, then energy will be transferred out of the system into the surroundings. If it's an endothermic reaction, then the energy will be transferred into the system, right, from the surroundings, like this. Now, let's this will look a little bit scary, but let's just think about this mathematically, or think about this logically. So my universe consists of these two parts, right? It consists of the system and it consists of the surroundings. Now, we said in the previous lesson that the change in energy of the universe is 0. Okay, so then if that's true, and the universe is equal to the systems and the surroundings, then in order for the change in energy of the universe to be 0, the change in energy of my chemical system plus the change in energy of my surroundings must also be 0. So if there's an increase in energy of my system, there has to be a corresponding decrease in energy of my surroundings. And that makes sense, right? Because if I have my system in here and energy is lost from the system, then where does it go? It goes to the surroundings. And how much of it? Well, all of it, because that's the place where it can go. Or if the system increases in energy, that energy has to come from the surroundings. Okay, so then any change in energy of the system must be equal to a corresponding change in the surroundings. That's just the opposite sign, right? If this guy gains, this guy loses. If this guy loses, this guy gains. And you might say, that sounds weird and confusing, Mahaffey. Why are you talking about this? It's because we can use this idea to understand chemical reactions and understand how much heat is being gained or being lost, and then therefore how much energy was gained or lost by the system. And that's important because if we want to look at something like a sandwich, we know that the sandwich has got chemical potential energy. You can eat the sandwich and then you can go jogging. But how much chemical potential energy does it have? It's difficult to quantify that. You can't take the atoms and kind of pull them apart from each other and put them back together with the little spring scales or something to measure how much attractive force there is between them. So you need a way to measure that. And the way that you can measure that is by basically burning the sandwich. See how much energy is being given off. And then by measuring how much energy is given off, you can then work backwards and figure out how much energy did the sandwich have. And this whole idea is called calorimetry. So calorimetry is this process. We take an isolated system, so we have our little chemical universe with a system and a surroundings, and we try to keep energy within that, so it can't get transferred from the surroundings out. Like there is no outer surroundings, right? This little chemical universe that we have up here is isolated. And when we do that, we can measure changes in temperature from a reaction in the surroundings, right? If we make the surroundings something like water, takes a lot of energy to heat up water, so we can do a chemical reaction in the system. And any increase in temperature of the water must be coming from the system. So the chemical energy change in the system, as I do my chemical reaction, is calculated by figuring out the thermal energy change of the surroundings. Because the thermal energy change of the surroundings is something that is relatively easy to measure. You did it in your Science 10 course. You did it quite early on, and we'll remind you how to do it if you've forgotten. So we can measure this thermal energy transfer, and we like to give it the variable Q. So it can also go by EK because it is kinetic energy. It's kinetic energy of molecules. Remember, when molecules heat up, they move faster, they get more kinetic energy. But we're going to give it the variable Q for our purposes here. So see if this formula is familiar to you here. Q, the amount of thermal energy, is equal to M times C times delta T. Q is equal to MC delta T. And what are those things? So Q is my quantity of thermal energy, which can be measured in joules or in kilojoules. M is my mass of whatever thing I'm heating up. For us, usually it's going to be water, but not always. And the mass can be measured in grams or in kilograms. And basically what's going to happen here is if you measure the mass in grams, you're going to get out joules. And if you measure the mass in kilograms, then your thermal energy is going to come out in kilojoules. And we can see with the units in a few minutes why that happens that way. C is the specific heat capacity of whatever thing I'm heating up or cooling down. It's often going to be water for us, but not, like I said, not always. The units here are going to be joules per gram degrees Celsius, or you might guess kilojoules per kilogram degree Celsius. And again, the unit that you would consider would depend on which mass unit you want to use. And because the joule and the gram are different by a factor of 1,000, right, each relative to each other, it doesn't matter which one we use. Then the temperature change here is your delta T. Remember that Greek letter delta just means change. And the temperature change is going to be measured in degrees Celsius. Luckily for us here, you don't need to convert these to Kelvin, because in Kelvin and Celsius, the unit step size is the same, right? 1 Kelvin degree is the same size difference in temperature as a Celsius degree, so we can use these changes in Celsius because they're changes. And then the specific heat capacity, RC, is the amount of energy required to heat 1 gram of substance by 1 degree Celsius. And you'll be given specific heat capacity values, or sometimes we want to calculate them, but they're not things that you'll have to memorize. And so you can find them in your data booklet. For example, the specific heat capacity of water here is 4.19 joules per gram degree Celsius. And the specific heat capacity of iron is 0.449 joule per gram degree Celsius. So relative to water, iron heats up very quickly and it cools down very quickly. That's why if you put a empty steel or cast iron pot or pan on the stove without water in it, it will get very hot very fast. But if you put even a small quantity of water in it, it will take much longer to heat up because it takes much more energy to heat up 1 gram by 1 degree Celsius. So let's try a problem. Determine the change in thermal energy, so that's Q, when 115 grams of water is heated from 19.6 degrees Celsius to 98.8 degrees Celsius. So this is my two temperatures, and I have to watch because in my formula, Q equals mc delta T, I need the change in temperature. So I need to figure out the difference between these two values. And if I take 98.8 minus 19.6, that gives me a delta T of 79.2 degrees Celsius. Now this substance is water, so I'm going to need that information to find my C. Luckily, I just wrote that down. My C is 4.19 joules per gram degree Celsius. And then we can plug in. I'm going to make sure to plug my units in because that's going to help me to see where the unit for Q comes from. So my mass was 115 grams. My C was 4.19 joules per gram degree Celsius, and my delta T was 79.2 degrees Celsius. So let's multiply those by each other. 4.19 times 79.2 times 115, and that gives me 38,162.52. Now, let's check out my units here. So I've got, remember, units cancel just like variables. I've got grams on the top, grams on the bottom. Those cancel. I've got degrees Celsius on the top and on the bottom. Those cancel. So this is going to come out in units of joules. Now, I've got way too many digits here. I'm only allowed 3 sig digs. So I can either put this into scientific notation. 1, 2, 3, 4, 3.82 times 10 to the power of 4 joules. That would be fine. Or I could put this into kilojoules. There are 1,000 kilojoules in a 1,000 joules in a kilojoule. So I have to divide this guy by 1,000. So that would give me 38.2 kilojoules. And either of these would be an acceptable way to report this answer. I might specify a unit that I wanted in, but for now, either of those would be fine. They've got the correct number of sig digs. They're equal numbers to each other. They're just in a different unit. Let's try another example. If the same quantity of energy were added to 100 gram samples of water, aluminum, and iron, which would undergo the greatest temperature change? Use data to explain your answer. Okay, so let's think about my formula. mc delta T, which would undergo the greatest temperature change. So maybe we should rearrange this to get delta T by itself and see how it depends on these other variables. So if I want m and c to cancel, I can divide by m times c, divide by m times c. Those guys will cancel, and delta T is equal to Q divided by mc. Now, what's going to be the same here? Well, the quantity of energy is going to be the same. The mass is going to be the same, 100 grams. The only thing that's going to be different is the specific heat capacity, right? The specific heat capacity for water, aluminum, and iron. So I can look up those values. Why don't we do that now? Water I know is 4.19 joules per gram degree Celsius. We've got iron right up here. It's 0.449. Let's find aluminum. Aluminum is 0.897. And if we want to really back up our value here, one strong way to do it would be to pick a quantity of energy. So let's say we've got 100 joules of energy that we're adding. Well, let's plug our numbers in here and see how the delta T is going to come out. And you can probably, you might be able to look at this formula and already figure out, based on where the C is, which of the delta T's is going to be biggest. But even so, I'm asking you to back up your answer. So I've got 100 joules is my Q, 100 grams is my M. Let's do water first, 4.19 joules per gram degrees Celsius. Maybe we'll set them all up here. So this would be water. Then we've got my aluminum, where the delta T is 100 joules divided by 100 grams times 0.897. And my iron, delta T equals 100 divided by, 100 joules divided by 100 grams times 0.449. So let's see what we get here. And these 100s are going to cancel, right? So it's just going to be the reciprocal of whatever C value we have. So for water, the temperature change, if I add 100 joules, 100 grams, will be 0.2, let's do 3 sig digs here, 238 degrees Celsius. Okay, so that's for my water. For my aluminum, 1 divided by 0.897. Temperature change here would be 1.11 degrees Celsius. That's for my aluminum. And then finally for my iron, 1 over 0.449. That gives us 2.23 degrees Celsius. So the biggest temperature change is going to be for my iron because it's got the smallest specific heat capacity. And that makes good logical sense because if the specific heat capacity is the temperature it takes to raise 1 gram by 1 degree Celsius, well then, if iron's got a low specific heat capacity, it should undergo a big temperature change because it doesn't take very much energy to heat it up. Then I've got some practice for you to try here, and then very quickly, because you're going to start on some calorimetry with your project this week. So what is calorimetry? Well, calorimetry is just the process of measuring energy changes within a calorimeter. So calorimeter has got a system, it's got a surroundings. And when you build a calorimeter, then you're able to monitor energy being transferred to the surroundings from the system or back to the system from the surroundings. And we can measure temperature changes in the water using Q equals MC delta T. Then we can calculate amounts of energy, right? If I know the temperature change of the water, I know the mass of the water because I put the water in there, and I know its specific heat capacity, then I can calculate an amount of energy. And so for a calorimeter, the energy gained or lost by the system will be equal and opposite to the energy gained or lost by the surroundings. And we'll pick back up on that idea next week.